So today we're going to continue working with this idea of substitution, that is change of variables, but this time we're going to look at definite integrals instead of indefinite integrals. So here's a common problem you might face. You want to integrate 0 to 2 of this function here, and I've drawn the graph here on the right, and so what we're trying to do is we're trying to figure out what this area is of this funny shaped region. And so basically what we do is we do the same thing that we did last time, is we try to find the antiderivative of it. So we start by first of all just trying to find the antiderivative. So we remove the bounds, we remove the 0 and 2, and we just concentrate on this problem of trying to, that is, we try to find the antiderivative. So we follow the steps exactly like last time. We choose a u, which in this case is probably going to be a good choice, is x squared plus 1. We compute the derivative, so we get 2x dx, and this tells me then that I can replace all of my dx's with du over 2x. So my integral becomes now the integral, let's see, I can replace inside of that cubed with a u. We'll keep the 4x there for now, and I'll replace dx with du over 2x. And after a little bit of canceling, what we see we're left with is 2 over u cubed du, which we can also write as 2 times the integral of u to the negative 3 du. So by reversing our power rule, we integrate this and we get 2 u to the negative second all over negative 2 plus c. And then we do our final replacement in terms of x. So what we end up with is negative, in parentheses, x squared plus 1 to the negative second plus c. So to solve our original problem, we can bring this down, and what we have here is we have an antiderivative. We found it in terms of x, so this means our original problem is going to be equal to negative x squared plus 1 to the negative second, evaluated at 0 and 2, which is just going to be 24/5. So that means 24/25 rather, is the area of this region we were looking for. Now this process really isn't so bad, but there is a bit of a slicker way that you can do this if you want to. What you can do is you can use the theorem here called the change of variables for definite integrals theorem. And what this theorem basically says here is you start out the same as if you were going to use a change of variables, but what you're also going to do is you're going to change your upper and your lower bounds as well using your substitution function. So let's see this in our previous problem. So again, we're going to use the same problem we had before, and so I'm going to choose my same u to be x squared plus 1, which gives me a du of 2x dx, which gives me a replacement that I'm going to replace dx again with du over 2x. So far nothing really different. The changes are that now what I'm also going to compute is I'm going to compute that u of 0, my lower bound, is equal to 0 squared plus 1, so 1, and u of b, my upper bound, which is 2 in this case, is going to be 2 squared plus 1, so 5. And now what I can do is now I can go, according to the theorem, and compute my integral in a different way. I can now say that this is going to be equal to the integral. I replace my lower bound of 0 before with 1. The upper bound of 2 now gets replaced with 5. And it's the same basic replacement process. X squared plus 1 gets replaced with a u. The cubed stays. The 4x stays for now. And I also replace dx with a du over 2x. And when I simplify this down, I now have to compute the integral from 1 to 5 of 2 over u cubed du. And these things are equal. So in order to compute this integral, I find my antiderivative again. So now again it's going to be 2 times u to the negative second over negative 2, but this time I evaluate at my new bounds 1 and 5. And when I substitute these in and I work through the computations, I again get 24 over 25. So I got the exact same answer. So let's think about why this happens. So originally I wanted to compute this integral from 0 to 2, and I know that geometrically this would have given me the area underneath the curve here from 0 to 2, and when we did the computation we got 24 over 25. And by doing the substitution, u is equal to x squared plus 1, what I did was I sort of transformed everything a little bit. So this u transforms the integral into this other integral, which also equals 24 over 25, and this time geometrically is the area under the blue curve from 1 over there until 5. Now even if these were drawn to scale, it'd be really hard to see that they gave the same area, but the fact is that they do. This transformation really just transforms areas, transforms the change that your integral does, until it's an easier thing to compute. Now this really shouldn't be that surprising that using integrals we can change areas of things until it's something more computable. I mean, that's the whole basis for an integral, right? So what an integral does is an integral says, let's chop this region up into a bunch of rectangles. Because of rectangles, it's easy to compute the area of, and let's just make them smaller. So all integrals do is chop up regions into really small things that are easy to compute. So it really shouldn't be a surprise that change of variables is again just chopping up regions and changing their shape until it's easier to compute. This is it for the day. This was our big lesson, is that if you want to change variables you can. If you don't want to change variables, you don't have to. So please try the problems on the other side of the sheet. Come to class with your questions, maybe get started on your homework so we can make a really productive day. As always, ask a question on Blackboard and take the quiz. I think you're really going to like it. Also, the key word from today's video is short.